So let's talk about important points in hydrocarbons. Okay. So you need to learn as a reactions here. So starting with Wurtz reaction. Got it?
Yeah.
So in simple terms, it is 2 moles of Rx when you react with sodium in the presence of ether, dry ether. Okay. It will convert into R and R plus 2 moles of NaX. This is Wurtz reaction. Got it? The mechanism can be both radical form as well as carb anion form. Okay. But what you need to know is that as much as 1 degree and 2 degree is concerned, you will get major part. Clear?
Yeah.
Otherwise, if it is 3 degree, you will not get it as major. For 3 degree, you will get it as one being alkene, the other being alkane. And this is called as disproportionation. Disproportionation. For example, let me show you with an example here. For example, if you have butyl chloride like this and another tert-butyl chloride or bromide like this with sodium and ether. Okay, so in that case, we will, instead of getting this as a major product, so this is minor product, while the major product will be disproportionated form, which means one becomes alkane, the other one becomes alkene. Okay, beta? This is what I'm trying to say. Hmm?
Yeah.
Second, rate of reaction. Rate of reaction for the formation of woods will always be greater for alkyl iodide, then bromide, then chloride. Correct?
Yeah.
Right. Okay. Second, another important point in this is CH4. CH4 is never uh, made as major product. So we cannot get this as major product in the Woods reaction. Major product via Woods reaction. Got
Yeah.
it? Next. Just like Woods, we have Woods fatigue reaction. Woods fatigue reaction. That is Rx plus PHX is reacting with sodium. Okay. And heat, or you can take it as ether. In that case, we'll get it as RPH. Okay. Now this will be major. The other parts will be minor. Okay.
Yeah.
This is called Woods fatigue reaction. Okay.
Yes,
By
sir.
chance, if you have chlorine and chlorine, then you are reacting with sodium and ether. In that case, instead of getting coupled product, you will get a double bond here.
Yeah.
Same way, if you already have a double bond existing with sodium and ether, you will get a triple bond here. CH triple
Yeah.
bond CH. Okay.
Yes.
Similarly, in case if you have double bond and Cl and Cl. Now what happens here is, if at all I make a double bond on this case, it will become an anti-aromatic ring. That's why it will go for 2 moles, and then those 2 moles will terminate with each other like this. So double bond here and double bond here. This is the way it will happen. Okay. Suppose if you have chlorine and bromine here, in that case, sodium and dry ether will give you 99% major product as internal termination. Correct? So this is about Korehouse synthesis. I mean, sorry, Woods-Fittig reaction. Next one is Korehouse synthesis. Check out Korehouse synthesis. This is mainly used for extracting unsymmetrical alkanes like alkyl halide. When you treat with multiple steps here. Step 1, you take reaction with lithium. Step 2, reaction with CuX. Step 3, reaction with some alkyl halide like CH3Cl. In that case, what you will get is RCH3, correct? Plus CuX again, and LiX will form here. Done? Okay. So here you can get an unsymmetrical alkene as a major product. Okay. Again, we don't have to get through the mechanism here. Just basic parts you need to know that alkyl halides plus lithium will give you RLi, and RLi when you treat with CuX will become R2CuLi, and this is known as Gilman's reagent. बस ये पॉइंट पता होना चाहिए अभी पास. Okay.
Yeah.
Next is rate of reaction. So if it comes to rate of reaction, it is usually 1 degree पे easily होता है. So 1 degree alkyl halide. So 1 degree Rx greater than 2 degree alkyl halide greater than 3 degree alkyl halide. Okay. That's it. This is what you will get. Next, fourth one. Kolbe's electrolysis. Okay. When it comes to Kolbe's electrolysis, two reactions will happen. One is at anode, one is at cathode. So what is the anode reaction? The R C double bond O, O minus, it will give R COO dot plus 1 electron. This is the anode reaction. Next, cathode reaction B. Okay. Water H2O will take 2 electrons to convert into H2 gas and release 2 OH minus. So this is anode and cathode reaction. This is what you need to remember. So it is also a free radical mechanism where this RCO dot will convert into R dot plus CO2. So if you get 2 moles of that R dot, so you will see alkane will form. Now, what are the important points here? pH in the solution, pH of solution increases during the reaction. Got it? pH of solution increases during the reaction. Okay?
Yeah.
Clear? Same way, CH4 cannot be synthesized.
Yeah.
Clear?
Yes.
What are the gases that are coming, beta? Carbon dioxide and hydrogen will come for sure. But if you have the alkene which is forming, the alkene can be gas as well. That is what you need to check. Important examples here. CH2, let's say CH2, COO minus and CO minus salt is present. And now if you perform Kolbe's electrolysis, you will get CH2 dot and CH2 dot, which and that plus 2 moles of CO2, and this would become CH2 double bond CH2, right? So this is the product. Clear?
Yeah.
Now the same logic can be done even with sulfonic acid also. So that means even if you have something like CH3 SO3 minus, with Kolbe's electrolysis also you will get this as CH3 and CH3 this way plus SO3 gas will come out. Understood?
Yeah.
Next one is decarboxylation. Now, what this decarboxylation is soda lime form. So this is soda lime decarboxylation. Okay, clear? So if
Yeah.
you have something like RCOO minus Na plus, okay, and that when you react with NaOH and CaO, got it?
Hmm.
This will become alkane, and the other part will become Na2CO3. This is soda lime
Hmm.
decarboxylation. Okay.
Yeah.
Now here the rate of decarboxylation, rate of SLDCl, write down, soda lime decarboxylation, will be proportional to, in fact it is proportional to stability of the carb anion. Stability of carb anion. So if
Yeah.
carb anion is more stable, that is what it is used to be. Important points here, what that can be asked is, what is the ratio of NaOH is to calcium oxide? We should take
Yeah.
this as 3 is to 1. Okay, minimum we need to take this as 3 is to 1. Done.
Yeah.
Right. Next, sixth one is Grignard's reagent. Grignard's reagent will also generate alkanes. It will happen via acid base kind. So in fact, if you have CH3 MgBr, CH3 MgBr can produce alkane as long as there is a sufficient proton is available. Like if you treat with phenol, if you treat with OH minus, if you treat with acid RCOOH, if you treat with ammonia, and next, in case if at all we treat with alcohol ROH, got it? And even if you have RSH, RSH here,
Yeah.
and even if you treat with this cyclopentadienyl, and lastly if you have beta diketones, in all these cases, right beta, because R minus is strongly basic in nature, it can give you CH4 here, CH4, 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 here also it will give you CH4, CH4, CH4 by taking H plus. What is the other part which is left now? The other part will be PHO minus here. Sorry, this is supposed to be H2O. With H2O, it
Hmm.
will become OH minus plus RCO minus plus NH2 minus plus RO minus plus RS minus plus cyclopentadienyl minus, and lastly double bond O and minus. Okay.
Hmm. Yes. Sir.
Next, seventh one. Now let us see about hydrogenation.
Sure.
Hydrogenation is another preparation for alkanes. This happens for alkenes and so. Okay. And you know that if you have any double bond here and then you react with any hydrogenated groups like H2 by Pt or H2 by Pd or H2 by nickel or Rann nickel, all of them will reduce this into alkanes by providing hydrogens. Okay. Now here stereochemistry is more important, right Arush? Here stereochemistry is more important, beta. And if you just try to recall it, in case if you have a cis molecule and I'm making a syn addition here, that will give you erythro. Okay, so cis usually looks like this. Okay, syn is an attack from same direction, both of them are attacking from same direction. Then the product you will get is erythro. This is erythro product. Okay, similarly, if you have trans molecule and I make a syn addition, so if you have like this and I make a syn addition, both additions are happening from same direction, then what do we get here is 3O. Okay, so 3O as in attaching groups are always opposite to each other in Fisher projection.
Yeah.
Okay, so when it comes to hydrogenation is a syn addition reaction. The syn addition reaction. So since it is syn addition reaction, suppose if at all I have a double bond here and I'm adding D2 in the presence of nickel, then what is the product you will write? You will write methyl here, and hydrogen here, and hydrogen here. Deuterium and deuterium here. Why is that so? Because this is a trans. Trans, when you make an as syn addition, you will get 3O. Okay.
Yeah.
This is about hydrogenation, which you need to know. Clear?
Yeah.
Within the hydrogenation, we have controlled hydrogenation also. Controlled hydrogenation is typically seen when you have a triple bond, and this when you treat with H2 in the presence of palladium barium sulfate, then you'll only end up getting cis molecule like this, H and H. This is cis molecule. Okay, cis as major. Okay, alternative. What are the alternative reagents? Alternative reagent is called P2 catalyst, which is nickel borate catalyst. Okay, or we can use palladium calcium carbonate, which will serve as the same purpose as barium sulfate. Okay.
Yeah. So 1 second.
हाँ बेटा.
Yes, sir.
So another controlled reaction is when you have a substituted like this. If you have a substituted alkyne, and that when you react with, you know, uh, sodium, sorry, lithium in liquid ammonia,
Yeah.
or sodium in liquid ammonia. In that case, we will get a trans molecule here. So H and H will get added like this. Okay, this is called Birch reduction.
Yeah.
This is called Birch reduction. So
Uh,
remember, Birch reduction can happen on triple bond. It can also happen on conjugated double bonds. Okay.
yes.
So if you have lithium in liquid ammonia, so in that case, you will get product like this. You will have hydrogen here and hydrogen here. Okay.
Hmm.
Next, what are the reactions you will notice in alkanes? Mainly, what are the chemical reactions you will notice here? Okay. We'll have substitution kind, isomerization, aromatization, combustion, pyrolysis. These are all the various reactions we have. Okay. So first is halogenation. This is the most important reaction in this case. Halogenation, which is radical substitution, free radical substitution. Okay. Now, how does this
Yeah.
work here? So overall reaction is like this. Alkane, when you react with X2 in the presence of H nu, will convert into Rx plus Hx. This is overall reaction. Okay.
Hmm.
It goes through various steps: initiation, propagation, termination. So what factors you need to remember is, fluorine is less, extremely high reactive. So fluorine dot is highly unstable form. Okay. And it is
Yeah.
highly exothermic.
Yes, sir.
So it is going to be highly exothermic. Okay. And uh, that's why this reaction would happen much faster. So in the case of iodine, I dot is, highly stable.
Hmm.
This is highly stable. It is least reactive. Okay.
Hmm.
So which means if you have CH4 reaction gas plus F2 in the presence of H nu, then it is supposed to be carbon black is what you will get, and HF. So it will get oxidized so much. While if you take
Yeah.
alkane plus I2, correct? In this case, you'll get Ri plus H2, but it is mostly reversible. Okay.
Yeah.
Now, if you want to reduce this reversibility, what you can do? Use oxidizing agents.
Yeah.
Oxidizing agents like, okay, HiO3, okay, HgO, to oxidized Hi2, I2. The Hi part will get converted into I2. Okay, sorry, this is Hi. In product जो भी HI बन रहा है, that will convert into I2. Okay.
Yeah.
While when it comes to chlorine radical and bromine radical, Cl dot is less stable. This is also less stable and
Yeah.
highly reactive, but not as much as that of uh, fluorine. But here is an important word that we use. It is less selective. Okay.
Yeah.
इतना less मतलब less selective as in out of 1 degree, 2 degree and 3 degree, its selectivity is relatively less in terms of stability. So
Yeah.
reaction ratio, or sorry, rate ratio, if you compare, okay, 1 is to 3.8 is to 5. Okay, this will be for 1 degree, 2 degree and 3 degree. Okay,
Hmm.
this is what is the rate will be for chlorine. For bromine, bromine is more stable. It is more stable. Okay,
Hmm.
less reactive. Okay, and highly selective. It is highly selective. So if it come to rate ratio, you will see it is 1 is to 80 is to 1600, which is for 1 degree, 2 degree and 3 degree.
Hmm.
Okay, beta.
Hmm.
This is what happens for halogenation. Okay.
Yeah.
As much as halogenation is concerned, this is what you need to remember. Okay.
Yeah.
Next. Next one being nitration. Okay. Nitration and sulfonation implies if you have an alkane, you react this with HNO3 and heat. Okay.
Yeah.
Get as CH3, CH2 and NO2. Okay. Clear?
Yes.
If you have propane like this, HNO3 and heat, what happens here is the bond can also break. In fact, you will get a nitro Okay, this nitro as well. Okay, you get ethyl nitro, you can get methyl nitro as well. Okay, just a second, beta.
Yes. Yes,
Right,
sir.
sorry. Right, this is about nitration. In nitration, carbon-carbon bond will also break. But when it comes to if it comes to sulfonation, okay, concentrated H2SO4 and heat. If you do that, you will get SO3H here and SO3H here, and bond breaking does not take place.
Yeah.
Okay,
Yeah.
clear? This is
Yes.
about sulfonation. Rate of reaction, if you notice, okay, rate of reaction if you compare. So it would give more product on 3 degree, then 2 degree, then 1 degree. Okay, 3 degree product would be more observed. Okay.
Yeah.
Next one is aromatization. Okay, check out. So if you have 6 carbons, on reaction with the reagent here, okay, that is Al2O3, Cr2O3, MO2O3, or V2O5 and heat. Okay,
Yeah.
this will convert into benzene. Clear?
Yes.
If you have one more carbon, extra carbon here, it will convert into toluene. Okay. And if you have 8 carbons, it will convert into this form or xylene. ठीक है बेटा? Right.
Yeah.
While aromatization also happens in cyclic structures, correct? Here the reagents used could be different. I mean, we can use the same reagents. The alternative reagents will be palladated carbon or sulfur and heat or selenium and heat. Okay. This will also convert this into an aromatic ring. Clear?
Yeah.
Even if you have this kind and you say, let's say selenium and heat, it will convert into naphthalene like this. Okay. And even if you have nitrogen also like this, sulfur and heat, it will convert into pyridine. So which is aromatic. So it will convert into an aromatic ring. Okay. Lastly, isomerization. Isomerization reaction is observed using concentrated HCl and AlCl3. So
Yeah.
if you have 4 carbons here with AlCl3 in concentrated HCl, you will notice that methyl will get uh, uh, substituted like this. So
Yeah.
in fact, if you have 5 carbons, let's say, okay, with AlCl3 and concentrated HCl, correct, what that methyl will keep on moving to multiple locations like this. यहाँ पर एक आ सकता है. Okay, clear beta?
Yeah.
Let me take 6 carbons to show more number of positions. ये आ सकता है. Okay, and we can have at the center also, this methyl can come at the center also, or we can see one more methyl like this also. Got it?
Yeah.
Clear beta? Sorry, this way also. Okay, so these are all the products that can be observed. Understood?
Yes.
Next, last one of the reactions is controlled oxidation. Controlled oxidation of alkanes. That includes, if you have CH4, let me put it this way, CH4 plus O2, you're reacting CH4 plus O2. If you treat that with copper and heat, okay, it will become CH3OH. Okay. If it is MO2O3 and heat, then it is, you know, HCHO, that is aldehyde. So in this case, you'll usually get aldehydes, beta. Correct. And if you have uh, MnOAC twice and heat, right? So then you'll get this as HCOOH, HCOOH, formic acid. Clear? So this is about controlled oxidation. The heat usually taken is 523 kelvins, okay, which is around 300 degrees Celsius. Correct? So this is the reaction which will happen. Along with that, in case if at all you react this with KMnO4, correct? Right, sorry, not with this one. Special reaction with KMnO4 includes tert-butane. Tert-butane with KMnO4 and heat. So that will convert into an tertiary alcohol form. Got it? This is with tertiary alcohol form. Okay. And lastly, controlled oxidation can also be shown as pyrolysis, also known as cracking. Pyrolysis or cracking. In case of pyrolysis or cracking, correct, you will notice that C6, suppose if you have C6H14, okay, and you treat it strong, you heat it strongly at around 773 kelvins, okay, clear. Usually for pyrolysis, zinc oxide is being taken, zinc oxide and 773. This will convert into C6H12 plus H2, okay, and at same temperature, if you crack it with a little high pressure, you might get C4H8 plus C2H6. The cracking can be done such a way that it can become C3H6 plus C2H4 plus CH4. So you can see the cracking can be done in so many different ways. So multiple number of products you will get. Okay. Arush, clear beta? Right. Now you see C1 to C4, usually alkanes are gases. Okay. Next, C5 to C17, these are liquids. Okay. C18 and greater than this one, these are all solids, waxy solids. Got it? Any doubt? Right. Now, typical reaction, how that can be asked in this case, like what are the products you can get and so. Okay. Usually, the most asked question is this one. How it has been framed here is like this. I take an ethyl chloride, okay,
Yeah.
then I treat with, let's say, first sodium and ether, I will get a compound A, okay,
Yeah.
and this compound A is being treated with Cl2H nu, got it,
Yeah.
and you will get a B, which is major product, clear, and that B is being treated with zinc and heat, you will get C, okay, beta,
Yeah.
and this C is being treated with uh, mm, C is being treated with, no, we'll do one thing. We can get this same C here, correct? The
Yeah.
C is a common factor here. So we can get the same C here, even with Kolbe's electrolysis. Let's say this is from D. So Kolbe's electrolysis will give you C as well. And now this D, when you treat with NaOH and CaO, it will give you E. Same decarboxylation. Okay,
Yeah.
clear.
Yeah.
And this E can also come from F, wherein the F will be H2 by nickel of one equivalent. Okay?
Yeah.
So we need to figure out what is A, B, C, D, E. Understood now?
Yes.
So this is the way typically the questions can be framed. Okay.
Yeah.
Hmm. 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 So let's see this. What is the product we can get? See, first one. ईथर के साथ क्या होगा बेटा? ब्यूटेन आ जाएगा. Woods reaction.
Yeah.
And after that, when you do chlorination, you can get chlorine at 2-degree position. And then zinc is just like Woods reaction. It is called Franklin reaction, but the reaction type is same, like this. These two connections will come across. Okay, clear? Now basically these two are getting connected by Kolbe's electrolysis. So that means I need
Yeah.
to have this COO minus, correct?
Yeah.
तभी तो वो दोनों connect होंगे. And
Yes.
this, if at all you decarboxylation is done, you will get an alkane here like this, which is same as
Yeah.
A, correct?
Yes.
And this A can come from F, which is from one equivalent. One equivalent matlab either this or it could be this. Any one of that is possible. Clear? Now question usually asked is this one. Okay. Number of
Mm.
number of possible reactants of F.
Yeah.
How many possible reactants of F? What are the possible reactants? This is 1. This one is 2. Okay. And the last one being this one, cis. So total answer is 3. This is how the
Yeah.
questions can be framed. Okay. Any doubt?
Yes, sir. No, sir. Understood.
Pakka na? Hmm.
Hmm.
Hmm. So this is how you will get uh, alkenes to react. Okay. Hmm. Now let's talk about the second part of it. Okay. Mostly when it comes to alkenes, this is how much you need to know better. Okay.
Yeah.
Second thing, before going into understanding of alkenes, right? How to prepare alkenes, right? Most of the time, alkenes are being prepared by making some kind of carbocation. Okay. So first we need to learn the concept and then we'll come across alkenes. Okay. Concept
Yeah.
is about when it comes to rearrangement. Okay. Carbocation stability and its rearrangement. Clear, beta?
Yeah.
So mostly you check out rearrangement on carbocations.
Yeah.
Okay. So for that, you need to check migrating aptitude. H is greater than aromatic group greater than 3 degree, 2 degree, and 1 degree. And lastly, methyl. Okay. This is the migrating aptitude typically. Okay. For example, if you have a positive charge here, so what do you migrate with? You will
Yeah.
make 1 to H shift. Hydrogen shift is been done so that the carbocation migrates here. Done? Clear,
Yeah.
beta? And what if the positive charge is here? In this case, no rearrangement, because if you have to rearrange first, you have to make 2 degree to 2 degree shift from 2 degree to 2 degree only. Okay. Similarly, suppose if you have positive charge here, correct, and an oxygen here, then rearrangement will happen on this side because oxygen can stabilize it. it will not go towards the tertiary side. So here also 1,2H shift will happen, correct? But it will happen on the oxygen side. Clear?
Yeah.
Because here it is more stable. Next, if you have a four-membered ring like this, and then you are expecting rearrangement, the rearrangement will happen to five-membered ring like this.
Yeah.
Clear?
Yes.
Similarly, if you have a seven-membered ring like this, and positive charge is here, correct?
Yeah.
So in that case, positive charge, sorry, let me take six-membered ring only. If you have a six-membered ring like this with a positive charge here, okay, it is at primary position. So we can notice that what can be shifted from here? The methyl can shift. So methyl will shift here. Positive charge can migrate here. So again, 1, 2, methyl shift will take place.
Yeah.
Right? This is a
Yes.
methyl shift which will take place. Okay.
Hmm.
If at all there is any uh, chance of getting a more stable carbocation with octet completion, like positive charge is here, in that case, positive charge has to somehow go to this position. For that, ring compression is expected,
Yeah.
like this, with oxygen OH plus, and which will eventually convert into keto form, like this. Okay,
Yes.
clear on this part?
Yes, sir.
Now let us see how do we make the alkenes. Okay, the first reaction, preparation of alkenes. First is dehydration reactions. Dehydration, okay, dehydration
Yeah.
of alcohols. How do we make dehydration? See, if you have any alcohol this way and you treat this with concentrated H2SO4 or concentrated H3PO4, or
Yes.
you know KHSO4 and heat, all of these would act like good dehydrating agents and convert that into an alkene.
Yeah.
So you can get alkene here like this. Okay.
Yeah.
But how does the typical mechanism take place? See, first will be protonation step. So this is the
Yeah.
first intermediate forming. Okay. And after protonation, you'll have carbocation formation. And carbocation formation is always the rate determining step. Hmm?
Yeah.
So from here, next step is rearrangement. Okay. After
Yes.
rearrangement on heating, it will undergo alkene formation. Okay. So
Yeah.
important step being protonation, then dehydration, then rearrangement, then deprotonation. These are very standard steps that you will notice during hydrolysis. Okay, beta.
Yeah.
Any doubt?
Not understood.
Okay. So see what are all the products you can get. For example, starting with this simple case here. Suppose I have uh, OH here. Let us start from here. And then I'm starting with concentrated H plus. As soon as you see here, usually heat will be always mentioned. Otherwise, also you think in terms of alkene product only. Okay.
Yeah.
The first step is always being formation of carbocation. Then the second step is about rearrangement. So hydrate shift will take place. 1 2 HS hydrate shift will take place. Once you get a proton transfer here, then you will get an alkene form. So you can get this alkene plus this alkene. Two alkenes are possible, correct? Now, the more stable alkene, this is less stable, this is more stable alkene. Okay. The
Yeah.
more stable alkene is usually major product. And this alkene has three substitutions. This alkene has only two substitutions. So the alkene with more substitutions, that is called as Shedzef reaction. Okay. Shedzef
Yeah.
reaction. And this one is called, Shedzef product. And this one is called Hoffman product. Got it?
Yeah.
So in this case, Shedzef product is being more or major product. Okay.
Mm.
See, if at all I have a compound like this with alcohol here, and then you react with concentrated H plus and heat. Okay. In
Yeah.
that case, what will happen? First, deprotonation will take place, positive charge will come here. From the deprotonation now, hydride shift will take place and positive charge will go here.
Yeah.
And once the positive charge moves here, now the ring expansion will take place. So 5-membered ring will become 6-membered ring. To give you the precise numbering, this is the numbering which you will get. So 1, 2, 3, 4, 5, 6. So between 1 and 6, we had a match. And at one position, we have two methyl groups. And positive charge has been shifted onto 2 position. And from here, you will notice that methyl shift will take place. So methyl will shift onto 2 position. One methyl is at 1 position with a positive charge. And thereafter elimination will take place.
Yeah.
Got it? This is how the product will be formed. Done.
Yes.
This is deprotonation, how it happens. Okay.
Mm.
Any doubt with this part?
Understood.
Okay. Next, this mechanism, right, where we notice that there is a carbocation forming first and then an elimination happening. So the above mechanism steps are E1 kind. So these are all E1 kind. Elimination E1 kind. Clear, beta?
Mm.
Next, usually for elimination here, you always need to check out which one is a stronger or a weaker base here. So whenever we have concentrated H plus, there is less or very weak base present here. So weak base usually prefer even mechanism. Hmm.
Yeah.
Now, otherwise we can have base which is moderate to strong also. Okay. So if we take
Yes.
a base could be, moderate form, or it could be strong form. Got it?
Yeah.
Clear? Moderate base, as in, something like, alcoholic KOH, RO minus, right? So if you notice this one, okay, it would usually give alkenes on heating. Alkenes on heating. When you heat it, definitely you'll get alkenes. Strong bases as in tert-butoxide, LDA, lithium diisopropylamine, NH2 minus, H minus. These are very strong bases. So these
Yeah.
strong bases will give you alkenes only. Even without heating, you will always get alkenes. Hmm?
Yeah.
Yeah, beta. Right. Now notice. So this type of mechanism is called E2 mechanism. So in E2 mechanism, let me take with an example. Suppose I have a chlorine here and I treat this with ETO minus and heat. Or you can also write this as alcoholic KOH and heat. Both meant the same thing. Okay. So what it does, it will try to remove chlorine and hydrogen simultaneously. Which hydrogen? This is alpha, this is beta. So beta hydrogen is being removed and chlorine is being removed as well. So it will happen in one step, and through that one step you'll get a double bond here plus ETOH. Okay. Since this has happened in one step here, and there are two molecules involved here, so that's why it is called E2 mechanism. 2 represents two molecules involved.
Yeah.
Right, Arush, clear beta? ये part clear
Yes,
है ना?
sir.
Now I could have got this alkene, or I could have got this alkene as well. The alkene could be here as well. Okay. So this is
Yeah.
Shezhev product. This is Hoffman product. Generally, if the base is not very big or large, then major product is Shezhev only. So this will be major product. Okay.
Yeah.
Next, in case if you have fluorine instead of this one, okay, and again I'll use alcoholic, KOH and heat. Okay. So in that case, I can get two products here, double bond here and double bond here. So this is Hoffman and this is Shezhev. This time, major product is Hoffman. This time, the major product is Hoffman. Okay. Here, this is still an E2 mechanism, E2 with carb anion character. So it will have a carb anion character. Next, in case if at all we have anything of why this is becoming major, because F is a poor leaving group. Poor leaving group. Other such groups, which give same reaction implied, fluorine, Nr3 plus, okay, Nr3 plus, and we have Pr3 plus, Sr2 plus, and so on. These are all the forms which you will get. Clear?
Yeah.
Any doubt?
Understood.
The other form is, even if you have a good leaving group, like chlorine is a good leaving group, but then you are treating bulky bases like O2 third butoxide. In that case also you will get two products. This is Hoffman, this is Shazef, while this one is major product due to bulkiness of third butoxide. So if you have more bulkiness also, you can get Hoffman product. Okay, beta.
Yeah.
What are the factors you need to know? E2 is an anti-elimination. So stereochemistry wise, you need to know that it is an anti-elimination. Okay. Okay. And it must have at least one beta hydrogen for elimination. So because it is a one step reaction, so everything should happen in one step only. Okay. So it is one step reaction. Correct. See how the questions can be framed here. Suppose if there is a chlorine coming here like this, and then there is a methyl going here like this inside. Now, if at all I ask you, with ETO minus and heat, what should be the product?
Yeah.
Cl minus is a good leaving group. while it is going from inside, the hydrogen has to go from outside. So both hydrogen and chlorine should be opposite to each other. And which you can notice here, because methyl is inside, hydrogen is outside. That's why this is how the major product will be. This is major. Okay. While if the same reaction is been again taken with making methyl this way, like this. Okay. Now what is a major product? Now this time problem here is hydrogen is inside. So it cannot make an anti-elimination. Therefore,
Yes.
this methyl remains the same. So hydrogen has to go from this other end. From here it has to go. Okay. So this is the major product. Clear?
Yes.
Mm. Okay. Mm. Next. In case if you have CH3, CH, Cl and Cl. Okay. And then you are performing an elimination reaction here. So ETO minus and heat. So you'll get CH2 double bond CHCl. So what will this become? Vinyl chloride.
Yeah.
Okay. Vinyl chloride cannot be eliminated easily by ethoxide. Okay. We require even a very stronger base. So that means with alcoholic KOH and heat, nothing will happen. But
Yeah.
in case if at all I use NaNH2 and heat, sodamide and heat, now this can help in eliminating that and converting this H and Cl can be removed, converting that into a triple bonded form. Okay, clear?
So
Any doubt?
also understood.
Hmm. Next,
Hmm.
these are all E2 reactions. These are all E2 reactions. Okay, but if at all I have, suppose if at all I have group like this, wherein I have OH here and double bond O here, and you know that OH, OMe, fluorine, clear, PHO, SR, correct, NH2, NR2 are
Hmm.
extremely poor leaving group. Extremely poor leaving group. So in that case, suppose if at all I take this case here, and then I react with let's say alcoholic KOH and heat. Now
Yeah.
definitely you will see elimination is happening. Now why that is happening? Because this is the steps that will take place. OH minus will first take away H plus from here to convert that into minus here with double bond O here. So what are we getting? We are getting a conjugate acid. They are making a conjugate acid. So this is a base and you are making a conjugate base. Conjugate base. Because this is an acid, it is giving away H plus. So what is left is conjugate base. And this conjugate base will be helping, because in this conjugate base you can see the resonance is helping it to form the conjugate base in the first place,
Hmm.
and that is the same group which will help in removing the OH minus and converting into this one, which is major product. So this is our major product. Clear?
Yeah.
I guess this part is understood, right? Next,
Yeah.
this kind of elimination is called E1CB mechanism.
Hmm.
E1CB mechanism. Okay. In case of
Yeah.
E1CB mechanism, conditions, what are the conditions? Must have poor leaving group. That is an important condition. Okay. Second
Yes.
condition, carb anion. Carb anion must be stabilized.
Yeah.
So the carb anion must be stabilized. Otherwise, E1CB mechanism does not take place. Okay.
Yes.
Hmm. Next example includes, in case if you have two chlorines here like this. Okay. So if at all I use zinc and heat, you'll get a double bond here. But in case if at all I use NaI acetone, if you use NaI acetone also, you'll get double bond here. Okay.
Yeah. Yes, sir.
In this case, the mechanism proceeds like this. You have sorry, Cl and Cl. Imanus is not a very strong base, so that's why it will make a bonding with chlorine, push electrons here, remove chlorine here, and that's how you will get it as a double bond plus ICl plus Cl minus. So this will be observed again as E2 mechanism case. This can be called as E2 mechanism with the double bond formation. Okay.
Yeah.
Next,
Yes, sir.
if you notice, the next is about addition reactions. These are all the preparation ones, beta. Okay. How do we prepare it? Clear? From alkyl halides and from alcohols, how do we prepare? We got this. Dekho. When it comes to uh, eh, reactions, chemical reactions, what do we need to know?
Hmm.
As much as the chemical reactions are concerned, we'll have C double bond C, because it will always invite an electrophile to accept. So pi bond will go attach on an electrophile like this, getting a carbocation. Correct?
Yeah.
And once a carbocation is forming, then a nucleophile will come and attack here, and you will get this electrophile and nucleophile. If possible, rearrangement is there, means rearrangement should also be done. This is called classical carbocation formation,
Yeah.
carbocation based mechanism. Okay.
Hmm.
But if it comes to chemical reactions here, an electrophile be such that it already has a lone pair on it. Suppose it already has a lone pair on it, it will not let the carbocation form completely. So what will it do? It will form a bridged compound like this with positive charge.
Yeah.
Okay, it will form a bridge compound. And when the nucleophile attacks, then the bond will break. So nucleophile will attack any of the direction, bond will break, and thereafter you will get the product. Now, when the
Yeah.
electrophile is supporting with its lone pair, it is called a non-classical carbocation.
Hmm.
Yeah, beta.
Yes.
Right. In which case, what would happen? That's what you need to know now. Check out react examples. Suppose if you have a double bond here and I'm making a reaction with HBr. So first thing what you do, you'll make an addition here, getting positive charge here. Correct? See, I could have got positive charge on this end also, but 2-degree carbocation is more stable. So this means you say it is following Markovnikov's rule.
Yeah.
So once you get here, you'll try to rearrange it. You can do the same thing by pushing a 1-2 hydrogen shift. Correct? So because from
Yeah.
here, the hydrogen got shifted here, positive charge will migrate here. Okay. And once you get carbocation, that's when the Br minus will be attacking on it and finally converts into a product like this.
Yes.
Then What if the same reactant is there? What is the same reactant is there now? But this time we are using peroxide. Especially with HBr, if you have a peroxide, then it will go for radical addition. So that means bromine will come here and radical will form here first. And that radical, on that radical, you will get a hydrogen getting attached. So what does that mean? We went through anti-Markovnikov's rule.
Yeah.
Okay. This is the product you will
Yes.
get following anti-Markovnikov. All right. Next, in case if you have, and our anti-Markovnikov rule is only observed with HBr and H2O2. With others like HCl and H2O2, it is not been observed. Okay.
Yes.
The other example is hydration itself. It is the reverse of what we have done it earlier. Suppose if you have like this, and then I'm treating this with now dilute H plus.
Yeah.
Dilute H plus means first the protonation will take place, positive charge will come here. Now it will, now on this case we'll have two positive charge and we'll get methyl shifted here, positive charge will come here. Therefore,
Mm.
we will get this as double bond.
Hmm.
Clear beta? Sorry,
Yes.
not double bond. Protonation. I mean
Yeah.
hydrolysis. Dilute use कर रहे हो ना बेटा, so alcohol
Yeah.
आ जाएगा.
Hmm.
This is the final product. Okay. Now देखो, these reactions have happened using uh, these reactions have happened using Markovnikov rule. Correct. There will be reactions which will happen via anti-Markovnikov's rule also. Got it? But let me
Yeah.
finish all the Markovnikov's rule as well as only classical carbocation used here. Okay. Suppose if you have CH3 C triple bond CH here, and then first mole I'm using is HCl. So with HCl, and I take only one equivalent. With one equivalent, we'll get this as CH3 CHCl double bond CH2.
Hmm.
Okay, this is the addition reaction following Markovnikov's rule. Okay,
Yes.
but if this is followed by second,
Huh?
which is HI, in that case, again the addition will take place at the same position where chlorine was there, and you will get this as CH3. This is the major product.
Yes, sir.
Clear how the addition has happened? Yeah.
Hmm.
And if you do hydration, correct? Hydration, if you do with H plus and H2O, it is difficult to make because carbocation is not formed easily, because
Yeah.
carbocation is unstable here. Vinylic carbocation. So instead of using vinylic carbocation, now what do we use? We use mercury, HgSO4 with dilute H2SO4, by which
Hmm.
now you will get OH getting added here, double bond CH2 here, and that would be forming into CH3, right? CH3, C double bond of CH3. So what do we get is keto form. Clear beta?
Yeah.
Next example is of non-classical carbocations. Suppose if you have a double bond here and then you are treating with, Br2H nu.
Hmm.
Okay. Sorry, not Br2H nu. I say Br2CCl4. Br2 CCl4 solvent. In that case, first you will get bromine forming here like this with a plus charge, and the
Yeah.
next mole of bromine is actually attacking on the more substituted side. And in that case, what do we get here is one Br will come here and the other one Br will be here. Finished. This is about non-classical
Yes.
carbocations.
Yes.
Any doubt here, beta? Right. Now, Br when it is adding, it is as anti-addition. Anti-addition. Since it is an anti-addition, you can expect some kind of elimination and all can be possible. Okay. So how does that happen? Check it out. So first you can have uh, let's see, cis or trans has been taken. Let's say like this: pH is here, CH3 is here, and then you are using Br2 and CCl4. So this is a cis molecule making bromine addition here, so which is an anti-addition. So cis and anti-addition. What does this happen? Again, it is the reverse of what we learned. So we learned earlier as cis plus anti-addition will give you trio.
Yeah.
Trans plus anti-addition will give you erythro. Cis plus right. Cis and syn elimination will give you erythro. Trans and syn elimination will give you trio. Okay. This is what you need to check. So this is a cis molecule going for an anti-elimination. So I should get trio. So that means both Br and Br should be opposite in Fischer projection, with one being phenyl, the other one being methyl here.
Yeah.
Okay.
Hmm.
Now, if you notice that the same compound can be formed, the same thing can be formed even on the opposite direction. That means we can have both BRs on the opposite direction here like this. So BR and BR here with H and H here. So what is this one? These two will be enantiomers. This will be pair of enantiomers. Okay. And both will be
Yeah.
50-50% each, because chances are both should be 50-50% each, and this is called as racemic mixture. Okay, racemic mixture.
Yes,
Are
sir.
you clear on this, beta?
Yeah.
Right. Okay. So this is the first part of the reaction for uh, alkenes as well. Got it? One
Yes.
second.